Hello, I'd like to do a brief video on the Atwood machine and tell you a few of the conceptual underpinnings to this type of problem. It's a pretty common physics example that you'll see perhaps on exams, and it's basically composed of this idea of a frictionless pulley, and you've got some mass. It's usually the larger mass here and then a smaller mass here. And what happens is when you let it go, the larger mass will go down, the smaller mass will go up like this, and your goal is to find something out about this system. And typically they'll ask you, what's the acceleration? So how do we solve this sort of problem? This is a Newton's law type of problem. And so you can be sure that in that you're going to have F equals ma as your governing equation. So this is going to be applied to the two different blocks. It'll be applied to this block, and it will also be applied to this block. And more specifically, what we're going to do is we're going to say the sum of the forces acting on any block is going to equal ma. So let's do this for the small block first. So I'm going to draw the small block down here like this, little m, and I've got a line going up like that. That's the cord that's attached to it. And so if I want to do a free body diagram, I can talk about the forces acting on it. So the tension from the rope is pulling it up, and the weight of mg is pulling it down. So this is for the small block. And if I want to do the sum of the forces equals ma, then I have to somehow add these forces. I have to add the tension, and I have to add the gravity, the mass times g. And so in order to do that, I have to really have a coordinate system. So I'm going to look at this block and everything that's going on with it in the context of the entire system. And what I'll do is I'll set up a coordinate system like this. I'll say going down is positive, where it's at is 0, and then going backwards is negative. Now, if I'm going to take this coordinate system here and apply it also to this block, I have to basically wrap it around, and this is very important. You've got to get this right, otherwise your whole thing will be wrong. Positive then means going up for the little block, that's 0, and negative means going down for the little block. Okay, so the positive direction is going to be like this. In that direction, it's going to go like that. So it's going to start the large block going down. And as the large block goes down like that, then what happens is we're moving in a positive direction. It will bring the little block with it. So if I apply this coordinate system here to this block in this diagram here, then what I have is tension is positive because it's going up, and mg is going to be negative. So if I write F equals ma, I say positive tension minus mg equals the mass of the block times the acceleration it will experience. So this is a valid equation for the little block. I have that right there. Now what I'm going to do is basically the same type of thing. F equals ma. Notice I'm using capital M. So this is the sum of the forces on the big block. So the big block looks like this. It's got tension there. Free body diagram is tension that way, and capital Mg going down. And remember, the coordinate system is like this. It's positive down and it's negative. And you can see that if you remember, this is how we did it. We set it up like that. It's naturally going to have the larger block fall down, the little block will go up, and so the direction it naturally moves in, I'm just calling the positive direction. All right. So now I do the sum of the forces, and so mg has got to be positive and tension has got to be negative because tension is pointing in a negative direction. So I have this equation, minus t plus capital Mg equals the mass of the big block times the acceleration it will experience. So now I've got these two equations that are boxed. And now the goal is, if I want to say, let's say, find the acceleration of the system, if I want to find out how the system will accelerate, I need to grind these equations down to something simpler. And so what I'm going to do is I'm going to copy this one here, like that. This is the equation for the small block. Hello, copy. And I'm going to put that down here, paste. And I'm also going to copy the equation for the big block. The sum of the forces equals ma for the big block. Off, you're done. And get this guy and pull this one together. Copy, Okay, and I'm going to put this guy down here, paste. And let me line them up like this. So what I want to do now is I want to eliminate one of the variables. So in this particular case, I can just add the two equations together. Negative tension will cancel with positive tension. And what I'll get is capital mg from the upper equation minus little mg from the lower equation equals capital Ma plus little ma, like that. And now what I want to do is solve for A. I'm trying to solve for the acceleration. It's this. And so I want to factor that out. So I'm going to say A times capital M plus little m. Okay, so I'm going to factor it like this. I can also factor out little g. So this is capital M minus little m. I have something that looks like this. And if I want to solve for A, I divide both sides by capital M plus little m, like that. Capital M plus little m. And then this term will cancel with this term. And then what I get is something like this. G times this fraction, the big mass minus the little mass, all divided the big mass plus the little mass. So this is the final result that tells us the acceleration of this Atwood machine, if we let it go, how this guy will accelerate downward. And a couple things to notice about it really quickly are just that up here we have a difference and down below we have a sum. So imagine little m equals 0. So if little m equals 0, then what we would have is an equation like this. G over m divided by capital M equals A. Well, you know what that is. That's just 1. And so the acceleration of the whole system would be just G going downward like that. That's if this mass doesn't exist. And so that's just this thing in free fall. One other thing to think about is this. What if capital M equals little m? Well, if that's the case, then capital M and little m, these guys are going to cancel each other. So you're going to have a 0 on top. And then what you'd have is something like this. G times capital M minus capital M. Let's just say they're exactly the same. This plus this, okay? And that's going to equal your acceleration. Well, this is just going to go to 0. And so it's going to be G times 0 equals A, and that means that A will equal 0. So there will be no acceleration at all. And that also makes sense, right? If this little m is actually the same size as this big M, then they're just going to hang there. Nothing will happen at all. So this is how we solve the Atwood machine using F equals ma, applying force diagrams to each of the two blocks, and making sure that our coordinate system is consistent. You just wrap it around. You wrap it around the rope as it's going, and it has to be pointing in the same direction. So if one block is moving in a positive direction, the other block also has to be moving in a positive direction. Hopefully that was helpful, and I wish you well in the exam.